Okay, thank you. Uh, First of all, I would like to thank you all for having me in your seminar. Yeah, I would have loved to come there, but I tried. And it was a bit difficult given the circumstances. Thank you for the introduction as well. Today, I'll be talking about an inhomogeneous background universe model in the form of a spherical large-scale underdensity or a void, and how the CMB temperature anisotropies would be measured by an observer located inside this void. So this was a part of this project was my master thesis, and I'm still continuing to work on it since I did my master thesis with Martin as well. So am I audible correctly or clearly?
Yep.
Okay. Great. So let's move on. Okay. So like any good presentation, I have this outline for you. So first we'll go through a bit of motivation of studying inhomogeneous universe models. Then we'll very briefly see what our chosen model looks like and some of its important characteristics. Then following that, the third part is we shall quickly go through the significant contributions towards the CMB temperature anisotropies in this kind of universe model. And finally, we can discuss the main focus of this work, which is the lensing of the CMB temperature anisotropies for a off-center observer in a large-scale void. So this would be part one, and depending on the remaining time after that, we shall enter the part two of the talk regarding exploration of different variations of the ALTB model and also of different parameters associated with the model. So let's start with a bit of motivation where we'll see a bit of introduction to cosmology course. So this plot shows the evolution of our universe in the form of a dominant density contribution with time or scale factor in the standard model of cosmology. It shows the three major phases of evolution, which is first is radiation domination. Then the second is matter domination after the matter radiation equality. And the third, that is today, it's the constant energy density domination. So hopefully everyone has seen this plot or a similar variation of this plot. Then moving on, so the constant energy density is one of the few explanations for the observed accelerated expansion of the universe in the late times. However, the Einstein's cosmological constant, which is used to model the dark energy, or this exotic form of energy, which is dumped as dark energy, it comes with a problem, which is the cosmological constant problem. This, in short, is the disagreement between the observed value of vacuum energy density, and that is the small value of the cosmological constant, and the theoretical large value of 0-point energy suggested by the quantum field theory. In short, we can say that the nature of this exotic dark energy dominating the energy budget of the universe today remains a mystery. So in search for easier alternative solutions to this mystery of dark energy, inhomogeneous background universe models were proposed to explain the accelerated expansion in the late times. So the idea is to simply replace the cosmological constant. So simply replace the cosmological constant, that Einstein's cosmological constant in the Friedmann equation by the spatial curvature density. And the spatial curvature is in the form of a large scale, I'm talking about gigaparsec scale spherical underdense region embedded in a flat homogeneous universe. This is modeled by using an ALTB or Lemaitre-Tolman-Bondi space-time metric, which we'll come to shortly. Then number one, the evolution of this underdense region would be perceived by an observer inside this region as accelerated expansion, which we want to explain using this model. And secondly, the inhomogeneity would start when the dark energy kicks in as the dominant energy density contribution. But yeah, life isn't so easy. So obviously the simplistic LTB models were ruled out to act as an alternative to dark energy to explain the accelerated expansion of the universe. It turns out that, like it was studied, that if one considers the model without any decaying modes, then a very large kinetic Sunyaev-Zeldovich signal is obtained as compared to the observations. On the other hand, if one manages to get a small KSZ signal by considering sizable decaying modes in the model, then the model would be ruled out because of Y distortions. So still, why should we be still motivated to study the LTB models, right? And point, I mean, the important note here, the LTB models are ruled out, but there is a variation of LTB model, which is called the lambda LTB model. So it's basically LTB with a cosmological constant that remains still a viable alternative to lambda CDM model. So why is it still interesting? So it turns out that by assuming an inhomogeneous background, we would be able to test the basic assumption about the large-scale homogeneity in the cosmological principle in the standard model of the universe. So this is a good test given the prospects of the incoming data from Euclid and other large-scale structure surveys. Secondly, we know from observations of the large-scale structure of the universe that certain empty regions called voids exist, because of which, which are known to cause distortions in the CMB observations. So distortions, for example, lensing, right? So using these inhomogeneous models, we would be able to test the effect of large-scale voids, if there are any in the universe, maybe even with the observer inside one of them. So that's a bit of motivation, at least for me, to study the effects of large-scale void. Now, let's see how exactly these voids can be described in terms of physics. So this is a visual aid that I find it easy to understand the model. So as I mentioned before, we model the inhomogeneous universe using the Lemaitre-Tolman-Bondy or LTB spacetime metric, which is given by this spacetime metric. The underdense region is spherically symmetric and radially inhomogeneous. And it is surrounded by the black region here is surrounded by it's the flat FLRW universe. So, and also it is important to note here that the LTB class of models is an exact solution to the Einstein's field equation of general relativity. So we want to see this model with an observer inside this underdense region. And so the normal question arises, where is the observer, where could be the observer situated? Normally, one can imagine the observer to be at the center of the void, but in that way, the observer would also be at the center of the universe, thus violating the Copernican principle. So this principle states that an observer does not have a special position in the universe. So this Copernican principle, in a way, advocates the cosmological principle of large-scale homogeneity and anisotropy. Sorry. So we move the observer off the center. So observer is not at the center, but still inside the void, and at some distance, let's say R0 from the center of the void and the universe. Now, given that I'm constantly talking about void and the flat homogeneous region outside the void, the next question is, how does the matter distribution look like in such a universe? So this here is the matter distribution function in one of the ALTB toy models that we have considered in this work. And it's, as you can see, it's a continuous function of the radial distance from the center of the void. So this R, right? And so this profile can vary according to the sum of the parameters that we can manually choose, right? So next comes the parameters in building this model. So we see the metric here again. Also, the Friedman equation shows the idea of replacing the lambda, the cosmological constant, by the curvature density, which is denoted by beta here. So this is beta is a curvature density parameter, which also appears in the metric. Then we have manually chosen alpha and beta. So alpha is the matter density parameter, and beta is the curvature density parameter, and they are only R dependent. R is the coordinate co-moving distance, right? And important difference to be noted here between the homogeneous and the inhomogeneous models of the universe is that all the functions and the parameters here in the inhomogeneous universe depend on R. So R, again, the co-moving coordinate. Now we have, as I said, it's an exact solution to Einstein's field equation. So we insert the solution which are parameterized in terms of eta, which we call it here as the conformal time. And we insert these solutions with some suitable initial conditions in the geodesy equations. And we solve them by using the ray tracing method. And we get some photon trajectories like these. So this figure is also for one of the toy models that I will show you in just the next slide. And the main thing here is that we can observe the bend in the trajectories. So we can see how the light travels in a straight line outside the universe, outside the void, then also in a straight line inside the void because of this matter density distribution. So you can see it's almost homogeneous inside the void and homogeneous outside the void. And there is inhomogeneity only at a small region near the boundary of inside and outside region. So moving on, so as I promised, so we are considering these two toy models in the ALTB metric. So the matter distribution for the two models look like this, where we have the physical distance from the center on the x-axis. And everything here is at time t is equal to t naught, which is the time today, or we can also call it the age of the universe. And yeah, so the physical distance or the angular diameter distance is given by this parameter here, r, so which is also one of the solutions to the Einstein's field equation, and which also appears in the metric as we have seen here. So I am not going into much details how the calculation goes. It's mostly GR, and now we can simply turn our pages to the CMB Temperature Anisotropies, which we will also go through very quickly because there is only one slide here. So, okay, first of all, let's see a schematic diagram for last scattering surface. So this dotted line is the last scattering surface. And this here is a single trajectory between the photon emission point on the last scattering surface and the observer denoted in the green dot. And yeah, I have obviously exaggerated the bending of the trajectory here. So it's not that strong effect, but it can be depending on the void size x naught and the observer position r naught from the center of the universe. And these two parameters would also come in at a later point in the presentation, and we'll see what are the effects of changing these parameters. So the CMB temperature anisotropies are mainly have three contributions in this model. So the first one is the primary or the intrinsic anisotropies present in at the last scattering surface, which are due to the inflationary phase of the universe. And secondly, we have the non-stochastic, what we call the non-stochastic temperature anisotropy contribution, which is solely due to the geometry of the universe. So this would be present even if the primary anisotropies are absent, that is the CMB is homogeneous. And this has been extensively studied in this paper by Alnes et al. So I would not go in this very much details. This mainly helps us to constrain the observer position R0 from the center using the CMB dipole and the observations. So what we'll focus in this talk is the combination of the first two terms, that is the third term, third contribution to the temperature anisotropy, which is the lensing-like contribution. So it's basically the lensing of the primary anisotropies and how we'll see it. So moving on, coming to the main focus of the talk, it's lensing of CMB temperature anisotropy. So we have seen this schematic before, and there is a very complicated formula for determining this lensing-like deflection angle. It's a subtraction. And well, theta LSS here, tilde is, it simply means that the theta LSS is shifted from the void-centric coordinate system to the observer-centric coordinate system. Right? And hence, there is a dependence on the observer position R0, which will play an important role in forecasting the lensing contribution later. Then, since we once we have this lensing-like deflection angle as a function of the incident angle C, so this is the angle of incidence of the CMB photons at the observer position, then we can calculate the lensing potential. So in the specific geometry chosen, lensing-like deflection gamma only has gradient modes. So this here is a case for when the azimuth is aligned with the Z direction. So this is the Z direction on which the observer is located. To generalize, we can consider a rotated coordinate frame. The change to the rotated coordinate system does not change the result though. So for the purpose of this talk, we will continue to use the frame in which only the m is equal to 0 component of the lensing potential is non-zero. So that is phi L0 here. And once we have the lensing potential, we can calculate 2-point correlation functions. So for just imagining for having a visual aid to the structure of these 2-point correlation function, we see the case for m prime set to 0. And in that case, we have defined the capital L, which is the subtraction of this L prime and L. And this denotes the off-diagonal elements in the correlation matrix. So the off-diagonal elements of the function appear in our case due to statistical anisotropy. Otherwise, the correlation function would be simply diagonal elements with the intrinsic anisotropy. And as we can see here, the correlation function decreases rapidly in amplitude for higher values of the off-diagonal elements. So as we go further off-diagonal, so this helps us with the numerical calculations of the SNR, the signal to noise, with Fisher forecasting. So in the sense that minimum number of off-diagonal elements that we can include, after which the result does not change. So we have seen the structure of the 2-point correlation function. Now, so we can move on to first see the relative contributions, relative levels of the 3 contributions that I listed before to the CMB temperature anisotropy. So yeah, the blue dotted line is the primary anisotropy. The orange and green are the non-stochastic anisotropy contributions, which is mainly due to the geometry of the universe. And there are two lines for the two toy models that I'm considering in this work. And finally, we have the lensing-like contribution here. So in this case, so you can see that we have divided the non-stochastic and the lensing-like contribution by 2L plus 1 because because they are only non-zero for m is equal to 0 mode. And yeah, that's why we have divided to better represent them by 2L plus 1. And this whole is a case for static observer. So realistically, the observer would also be moving with the CMB rest frame, which would change the lowest multipoles in the non-stochastic anisotropy. So it would further suppress it because a boost is degenerate with the lowest multipoles. Now we can look at the implications of the 2-point correlation function. So we have seen that in ALTB model, there is mainly the geometrical contribution to the CMB temperature anisotropy in case of a static observer. So here, in case of linear order in lensing, so this phi represents lensing. So linear order in lensing, we have non-vanishing diagonal elements of the correlation matrix and also excited off diagonal elements of the correlation matrix. So with the structure of the correlation matrix that we saw here, we can see that there exists correlation between every neighboring multipole of, so we can say that L is correlated with L plus minus L for all values of capital L. While on the other hand, in FLRW model considered with a kinematic contribution, that is with a boosted observer. So this has been studied in the paper by Cuisine et al. And so there they observe that at linear orders in beta, which is the boost of the observer, we get vanishing diagonal elements and the excited off diagonal elements only for capital L equals to 1. That is, correlation exists among only L and L plus minus 1 mode. Then they repeat the calculation at higher orders of boost, and they observe that they have non-vanishing, in this case, they have non-vanishing diagonal elements and excited off diagonal elements only for the capital L equals to N, where N is the order of boost velocity in which the calculations are done. So the point is that the correlations do not exist among every neighboring multiple, right? So this gives us an important and exciting signature of the geometric effect due to LTV models. So if we observe correlation among all neighboring multipoles, we see it as a sign of the geometrical contribution. And this helps us distinguish between FLRW universe and an inhomogeneous universe. And finally, having all this, having the correlation function, we can predict the signal to noise by Fisher forecasting. So again, we have the results for two models here, model A and model B. So I forgot to mention this before, if it was not clear from the matter distribution. So the difference between model A and model B is that in model A, we have a more smoothly transitioning matter density from inside to outside region of the void. And in model B, it's locally homogeneous inside the void. Then there is a sharp transition to the outside homogeneous region. So that's all the differences there between model A and model B. So now that was the framework that was set for forecasting the lensing contribution to the CMB lensing. And now that's the end of part 1, basically. So we can move to part 2, and that is we will see effects of exploring different variations of the LTV models, as I mentioned. and also the effects of varying different parameters associated with this model. So that is mainly we are going to we study the observer position R naught and the void size X naught related to the LTV model. So the first part of this exploration is setting an effective approach for calculating the signal to noise. So we have seen that the lensing potential with the numerical calculations of LTB model have this form. So we can easily see that it can be modeled by a power law function, so which we have here, and this is called the effective approach. So here we have three parameters that we need to focus on. One is A, which is the amplitude of the lensing potential. Then the second one is alpha 1, which is the slope of the lensing potential. And finally, we have L cutoff. So this L cutoff means that at what L value, at what multiple, we can cut off this effective approach model and set the rest of the values to 0, so that it does not affect the signal to noise calculation significantly. So the contributions would be negligible, and it would affect the signal to noise we get after some L cutoff would be the same. So fixing the L cutoff, for example, if for now, let's fix this L cutoff to the value of 2, we'll see why. And fixing the L cutoff, we remain with we are with two remaining parameters. The first is the amplitude, and the second is the slope of the phi L0. So there is direct signal to noise dependence on these two parameters. So the dependence on the amplitude is quite trivial. It just the signal to noise simply shifts with the shift in amplitude, just linearly or directly proportionally. And for the dependence on alpha 1, we'll see in this, we will see how the signal to noise depends on the slope of the phi 0. So here I have plotted phi 0, the lensing potential for various sizes of the void with fixed ratio of observer position to the void size. So the phi 0, the lensing potential from the numerical calculations are plotted in the solid lines, and the dotted lines denote the effective approach lensing potential curves. So we basically fit the numerical curves with the effective approach curves to extract the dependence on slope and amplitude for realistic LTB models. And as I mentioned before, for L cutoff, we only use L is equal to 2. That is, we use only the first two multipoles for calculating the slope, that is the alpha 1. And so we can see that after that, the lensing potential further decays down. So there is negligible contribution from that. And yeah, and one thing to note here that, okay, with increasing void size, the slope also changes. The slope alpha 1 also changes, and it changes rather weirdly. So at some high value of void size, we have a higher or lower slope than the rest of the values. So it decreases, it increases, and then it increases further, and then it decreases. So we'll see. Why this is so. So first of all, we need to understand why we have set L cutoff to 2, and this plot would hopefully make us understand why. So here, let's go step by step. So first of all, on the y-axis, we have the signal to noise for a particular L max value chosen. So in the signal to noise curve, we saw that we have plotted the signal to noise for this is the cumulative signal to noise, by the way. So we have plotted this cumulative signal to noise until some values of L max, that is around 3000 or so. So we take we take a value, middle value, which is 1000. On the x-axis, we see how this signal to noise depends on the slope of the phi L0 function, that is the alpha one. And finally, so we have the third parameter here, L cutoff. So let's begin with L cutoff of 1. That is, we use only the amplitude of the dipole amplitude in the lensing potential to calculate the signal to noise. And in this case, if obviously you can see that from this formula, we have L equals to 1 to the power alpha 1. So the dependence on alpha 1 goes away. And for the rest of the multipoles, we have set the lensing potential to 0 manually. So this here, the blue dotted line is the case for L cutoff of 1. Then if we increase the L cutoff, we have increasing signal to noise for a given particular slope of the phi L0 function. And so yeah, now we come to the lowest slope of this plot. So we have varied the void size from 100 to 5000 megaparsec. This is 5000 megaparsecs is already quite high a void size to be considered, given that the total co-moving distance to the last scattering surface is around 11,000 megaparsec. So yeah, we obtain the low value of the slope. And we can see that for this, there is a simple solution to calculate the signal to noise correctly or accurately, that we just have to consider a higher L cutoff. So at 3, for example, you can see that the signal to noise values seem to converge after some L cutoff of 10. So if we consider, for example, an L of the phi L0 function until L of 15, let's say, then after that, it will stop affecting the signal to noise. And then why is the slope for this void size so abnormally low? So this is because this gamma tilde function, which is dependent on theta LSS tilde, and this in turn depends on the observer position. So which we increase the void size and hence also increase the observer position, because as I mentioned, we are keeping the observer position to the void size ratio fixed. So naturally the observer position also increases, and hence there is this geometric dependence on the theta of the theta LSS tilde, which comes in the gamma tilde on R0. And this, all of this information, so this is numerically observable, that only the dipole amplitude is affected by the void side change and not the quadrupole. And so the quadrupole just keeps increasing with void size, but dipole has a strange trend due to variation of R0. And all this information for a L cutoff of 2. So we have only considered the 2 starting to multipoles of the lensing potential. All this information is summed up in this plot, where we see the effects of changing the void parameters, R0 and X0. R0 is the observer position, X0 is the void size. So we see the effects of changing these parameters on the effective approach parameters, that is the phi L0 amplitude and the phi L0 slope alpha 1, and hence indirectly on the signal to noise. So let's see what these plots are for the red and the yellow curves. What we have done is we have varied the void size without changing the observer position. So how do we keep the observer position fixed? By just keeping constant the ratio of observer position to the void size. And in the rest of the 2 curves, we have fixed a void size to some certain value, and we have varied only the observer position. And yeah, so we observe this strange trend again, as mentioned before, due to the dependence on the observer position in case of the fixed ratio of observer position to the void size. But we haven't got this trend in the in the other two curves because we haven't went that far in the observed position with fixed void size. So overall, this sums up the effect. This plot can sum up the effect of these two parameters on the calculation of signal to noise. And now we want to see this kind of plot for other variations of LTB model. So the next one is lambda LTB model. So this one is just LTB model, as I mentioned before, with a cosmological constant. So the Friedmann equation looks like this, with the red part indicating the LTB Friedmann equation, and we just add a cosmological constant density contribution to this, to the H perpendicular squared. And the solution to the Einstein equation can again be written in terms of the parameter, the eta parameter, which we call again the conformal time. And we get the solution in terms of Weierstrass elliptic functions. So this makes the ray tracing method even more complicated than the LTB. LTB is a piece of cake after this. So yeah, we still, so this here is a work in progress. I thought like this would be done by now, but yeah, there are new problems keep coming up every now and then. So hopefully I will discuss the final results soon as well. Then we do have some results for this model. So instead of changing the void size or the observer position, here we show the effect of changing the lambda contribution in the lambda LTB model, and also of tweaking the H0 values. So let's focus on the left-hand side plot here, which is for a relatively large void size, and the right-hand side is for a relatively lower void size. So if we see, we have 3 points here in the corner, which correspond to 3 different values of omega lambda, which are almost close to 0. So the omega lambda equals to 0 indicates the LTB model, that is without any lambda. Then as we increase the omega lambda to, let's say, 0.7, which is the case for a lambda CDM model, we get the point all the way over here. And when we change the H0 parameter, then the point comes a little bit closer to the LTB model, but not all the way close. And this plot here is mainly indicating the difference between LTB and lambda LTB model, which we need to account for in case we can. So we do want to extend our LTB calculations to the lambda LTB calculations, but to the lambda LTB model. But since it is numerically much difficult to calculate than LTB, we are hoping that this difference would allow us to continue the calculations with LTB, continue our parameter exploration with simple LTB model, and then simply extend the results to lambda LTB model. So as I said, this is a work in progress, and the parameter space exploration is in progress as well. So we also hope to get a similar plot to this one. This is for LTB model. And yeah, so let's move to the next part. Yeah, we have seen this. So let's move to the next part, and this will be the final topic of my discussion today, which is the limiting cases of LTB model. So mainly we shall see here 2 extreme limits of the matter distribution scenario. So the first one is called a thin shell void. So this has been studied or proposed by Thompson and Wishniak in 1987. And the idea here is that instead of having a continuous matter density distribution, we have a discrete one. So we have this void region, which is completely empty. There is no matter here, and hence it is described by Minkowski spacetime, and it is surrounded by homogeneous and isotropic cosmology, described by the normal FLRW metric. And the idea is that matter inside the void is concentrated in a thin shell at the boundary between these two different spacetimes, and hence the name thin shell void model. And what so we also want to compare our LTB results to this limiting case, so that we know that having a continuous function, we can also get, we can basically just estimate the correctness of our LTB results with this simple analytic model. And here we just assume that the void boundary is expanding with time t. So this also has been studied in these two references, so why this sigma parameter is of order 1. And so hence with a moving void boundary, if we consider observer co-moving with the void boundary, we have a velocity of the observer, right? And then the deflection of the CMB photons due to this inhomogeneous transformation is calculated by having two Lorentz boosts. So first one, two consecutive Lorentz boosts. So the first one is to convert the photon 4 momentum from this region to the frame of the void shell. And the second Lorentz boost is to convert the photon 4 momentum to the coordinate frame inside the void. And yeah, so this calculation has also been done in the Thomson and Vishniak reference that I mentioned here. And finally, we are able to calculate the deflection angle, and hence we can also calculate the gamma, so as to compare with the LTV model. And so this also is a work in progress. The next one and the final case is the second limiting case, which is the Swiss cheese void, which has been extensively studied in, again, the same reference as earlier, Cuisine et al. And here the idea is that void is described by a static black hole metric, the Schwarzschild metric, embedded in a homogeneous and isotropic universe. So naturally, there are some boundary conditions to be met. Also, in the other limiting case, we have to consider some boundary conditions. Then instead of the matter being concentrated at the edge of the void, at the edge in a thin shell, the matter is concentrated at the center in the form of a black hole. Hence the name Schwarzschild metric, Schwarzschild void. And so here, Cuisine et al., they calculate the same function, that is the deflection, lensing-like deflection angle for an off-center observer, and they have the following form. So the first two terms here are degenerate with the kinematic effects, that is for a boosted observer. This has also been studied in this paper. And secondly, the second term here and higher order terms, they are due to purely geometric contribution. So in a way, we can see that there is dependence on the void size x0 and the observer position r0 also here. So if we fix the ratio of the observer position to the void size, that is r0 over x0, then we have dependence on only the void size. On the other hand, if we fix void size, then we have only the dependence on the observer position. So hopefully we can also recreate the parameter exploration plot also in this case, so that again, we want to confirm the correctness of the LTB numerical results. And yeah, this brings us to the end of today's talk. So in summary, we saw a little bit of motivation. So why we should study LTB. Basically, we have to prepare for the new data that will come from the future surveys, more inclusive surveys. Then secondly, we have seen the LTB model, which is basically a continuous transition in terms of matter density from a surrounding homogeneous flat universe to the inhomogeneous region inside. Finally, with the 2-point correlation functions, we also saw by its implication that we have an interesting observational signature of the geometric contribution as compared to a model, the FLRW model, with only the boost of the observer contribution. to the lensing effect in the CMB temperature anisotropy. Then after in the second part, we see to study, we see what happens when we tweak the void parameters, mainly here the void size and the observer position, and then the effect on the calculation of signal to noise forecasting. And finally, we aim to extend this study to more realistic models like lambda ALTB, which I also discussed very briefly because, again, it's a work in progress. So thank you very much. And I'll take questions now.